Like I said, what is the actual problem? So if you remember how a router works, you will recall that every packet has a destination IP address, right? And when I say of IP, I always mean that both IP version 4 and IP version 6. So today, IP version 4 and IP version 6 will be handled separately, and I'll clearly mention which concept applies to which protocol. But at a high level, this applies to all the IP protocols. Every IP packet too has a destination IP address. So based on that destination address, the router decides where to send the packet. In other words, it selects the next hop. So to do this, the router uses a large table called as the routing table. So to do this, the router uses a large table called as a routing table, and this table doesn't contain millions of individual IP addresses, but instead it contains IP prefixes. Okay, so I'll go into much more detail about this in my routing session. So if you have missed that, so I'll recommend you to watch that video as well. So let's see. So when I talk about layer 2 protocols, I'm talking about frames specifically. So when I talk about the IP layer 3, I'm talking about packets. So now an Ethernet frame also needs a destination Ethernet address, the MAC address that we are talking about. And this is where the real question comes in, like where does the router get the destination MAC address from? So at this point, the router only knows about the destination IP address and the next hop IP address from its routing table. But to put the packet into the wire, it needs the next hop's router's MAC address actually. So exactly what the slide shows you here, the destination Ethernet address is what we exactly need. So the exact problem is mapping of an IP address to a MAC address is the actually today's topic. Okay. So how do we find an Ethernet address for a given IP address? So for that, we need a method that can, for a given IP address, tell us the corresponding Ethernet address. So this is required not only by routers, but even a normal system like your laptop or your PC needs this information when it wants to communicate locally on the network. Okay. So whenever a device wants to send a traffic to an IP address on the same LAN, it must first know the Ethernet address of that IP. In IP version 4, the protocol that solves this problem is called ARP. ARP is nothing but the address resolution protocol. And in IP version 6, this function is handled by the neighbor discovery, often abbreviated as neighbor discovery, that is ND. So both ARP and neighbor discovery provide the same basic function. They give you the Ethernet address for a given IP addresses. So however, even though their goal is the same, they work quite differently. So let's take an example over here. So how do I get the Ethernet address for a given IP address? So let's start on a local network with a single host that wants to send a traffic. First of all the sender must have an IP address. In our example, the sender has an IP version IP of 192.0.2.18/24. The sender also knows its own Ethernet address, so that part is quite easy. Okay, so now the sender wants to send a packet to the destination that is 192.0.2.33. So what does it know? It knows the destination IP address. Okay, it knows that this IP is on the same /24 network, but it doesn't know the Ethernet address of the target, and that is the key problem. Okay, so to actually send the packet on the Ethernet, the sender needs the destination MAC address, and this is exactly what is missing. So the sender has to find out what is the Ethernet address of 192.0.2.33 over here. And to solve this problem in IP version 4, we use ARP, that is the address resolution protocol. So as the name already says, ARP is a protocol, and ARP was designed only for Ethernet, and it was designed only for IP. It was intentionally kept quite open and generic. So in theory, you can say that ARP can be used to map different network layer addresses to different link layer addresses. So in practice, you will almost exclusively see ARP used over an IPv4 over Ethernet segment only. So that's where it really matters today. So how does ARP actually work? So at a very high level, the ARP uses the broadcast capability of the Ethernet. The sender broadcasts an ARP request to all the systems on the local network. And in that request, the sender includes its own MAC address. Includes its own MAC address. I'll just show it to you in the slide also. 1 second. Yeah, its own MAC address. Then its own IPv4 address and the target's IPv4 address it is looking for. And then it simply waits. And the idea behind it is that if anyone on the segment knows this IPv4 address, then please answer that. So the system that owns the target IPv4 address responds with an ARP reply, sending back its Ethernet address. And that's the Ethernet address is exactly what the sender was asking for. Okay. So we'll look at that ARP request packet here. So as mentioned earlier, ARP is not designed only for Ethernet. It is not only limited to IPv4 either. Okay. So it was designed to be generic. However, in practice, we mostly see that ARP is used with Ethernet and IP version 4, which is what we are looking at here commonly. And the first fields in the ARP packet describes what kind of an environment we are operating in. Okay. So the first type is the hardware type, that is the Ethernet that you all know. Then the protocol field that we have, that is IP version 4. Then there is a value field where there is ether type for IPv4 in an Ethernet type. Next, we define the address length also. Okay, there is hardware address length, that is the Ethernet MAC address that we are talking about, that is 42 bits, or it has 6 octets to be precise. And then we have an IPv4 address field also, that is your 32-bit field, which has the 4-octet value. Then comes your operation field, where it is already set to 1. And the interesting part now, the router specifies the sender, that is MAC address, and the requester's IPv4 address also, right? So we do not know the target's MAC address yet. So the target address is left blank here, like you can see in this Ethernet frame. So this is now my ARP packet, and I'm putting it into an Ethernet frame right now. So since I don't know where to send it, I simply broadcast it. And broadcast is nothing but I'm setting all the ones to FFF, which is the broadcast address for the destination Ethernet address or the destination MAC address that we don't know. Okay. And for the source MAC address, it is my own MAC address. And then the ether type we are keeping is 0x0806. That is the ARP. ARP has its own ether type. So after that, I send it out, broadcasting it to all the systems over the Ethernet segment. All the ARP requests are sent out using the Ethernet broadcast, like I said. But that means that every station on the LAN receives them and has to process them. So because it's a broadcast, the frame doesn't get filtered out by the network adapter. It has to be passed up to the CPU and inspected. Okay. So this is the main disadvantage of it. So now imagine if a large peering LAN like DE-CIX India that we have with thousands of stations, these are connected. So there is a constant background noise of our broadcast happening all the time. And on a LAN of that size, this can become very problematic because each and every ARP request must be processed by every station. And each station then checks whether the target IPv4 address matches its own. So that check also causes the CPU cycle. If the address does not match, the ARP request is simply discarded. So if it doesn't match, then the target sends an and if it does match, the target then sends an ARP reply to the requester. So like we say as seen the ARP request packet. So let's see how an ARP reply packet also looks. So in the ARP reply, the packet almost looks the same. Okay, the operation field is now set to 2, and which indicates a reply. Everything else in the header remains unchanged. So we now include the original target's Ethernet address. So this information that was requested, and the part highlighted in the red shows the key details that what the sender wants to tell the requester. So in the reply, the target address fields actually contain the requester's Ethernet and IP version 4 address. So remember, we are sending the packet back, so the values are swapped compared to the request. Okay. So the part highlighted in the red, like I said, is the key detail where the sender wants to tell the requester. And and in the Ethernet segment, the address field, we put the MAC address that the requester needs in order to send the IP traffic back to the original host. So again, we'll see how this fits into the Ethernet frame. Again, the ARP packets goes into the frame somewhat like we seen in the ARP request packet. So the destination address here is the requester. Okay. Then the source MAC address is of the sender, and the ether type is set to 0x0806, like we had already seen. So you might wonder why this information is included again inside the ARP packet, even though it's already in the Ethernet frame, right? So the reason is that another system can reply on behalf of someone else. So this is also called as a proxy ARP, and it is not good when you run a big LAN segment. So I won't go into those details yet, but it is still possible. So because of that, the source MAC address in the Ethernet header and the information inside the ARP payload can be different. Okay. So the requester only looks for the ARP payload to fill into its ARP table, because that's where the requested information actually is. So you would say on which layer ARP should actually be functioning. So we talked about layers earlier also, about the layers in the IP protocol stack. So the question now is on which layer does the ARP will operate. So ARP works directly on the top of Ethernet. So you could place it at layer 3. So you can place it at layer 3, but it's not restricted to IP version 4. So, but at the same time, it is not really a part of the internet layer. So the best way to describe it is like ARP sits at layer 3. Okay. ARP sits at layer 3, but it is not an IP packet. It has its own protocol at layer 3. Okay. So that is ARP for you, and how IPv4 host and router learns the Ethernet address for a given IPv4 address. So that was ARP. Now we will move on to IP version 6 neighbor discovery. So now let's talk about IP version 6 ND. So the problem is basically the same. I want to send an IPv6 packet from my own host, and for that I need to know the Ethernet address of a system I want to send the packet to. So the question is, what is the destination Ethernet address and how do we find it? Right? You can see in the slide also that I want to have the destination address of one of the requested IPv6 address. So if you remember the discussion we had about the broadcast and the multicast, IPv6 does not use a broadcast anymore. It was removed because in large LANs, broadcast traffic creates too much of noise. Instead, IP version 6 uses multicast. So every IPv6 host joins one or more multicast groups, and it tells its Ethernet adapter that I want to receive traffic on this specific multicast addresses. Okay. So the network adapters can join many multicast groups. So the host receives only traffic it needs, and not everything like the broadcast that is broadcasted to the entire stations. Okay. So for each IPv6 address on an interface, the host joins a special multicast group called as the solicited multicast address, right? So this is also defined in RFC 4291. So if you want to check that out, you can click on the link after we share you the slides, and you can refer to exactly what is defined in that particular RFC for this multicast address solicitation. So this IPv6 multicast address starts with FF02, okay, and it includes the last 6 bytes of the IPv6 address, okay, and for every IPv6 address there is a matching multicast group. So this IPv6 multicast address is mapped directly to the Ethernet multicast address. So for instance, Ethernet uses 48-bit addresses, right? And IPv6 uses 128-bit addresses. So this mapping is required and it exists. Okay. So because of this mapping, V6 does not need broadcast. So by using multicast, it is possible to discover a specific neighbor. So now let's see how the packet looks like. So here we have a standard ICMP V6 packet. So it is basically an IP version 6 packet with an IP version 6 payload. So in this packet, you can see, the source IPv6 address is the requester, and the destination IPv6 address is calculated multicast address, and the last 6 digits comes from the requested IP version 6 address. Okay. So the requested IPv6 address itself is placed inside the ICMP version 6 part as the target IPv6 address. Okay. So there is an option, also an option in the IP version 6 that carries the Ethernet address of the requester. Okay. So this is how IPv6 neighbor solicitation message looks when a host wants to discover the Ethernet address of a neighbor. Okay, so if you look closely, it contains basically the same information that we had seen in the ARP packet. Just it is structured in a different way. The source address, IPv6 address, the destination IPv6 address, then the flags and the length. Okay, so it is just structured in a different way when you see the Ethernet frame for the IPv4. And now again, the packet is put into the payload of an Ethernet frame. And the main difference here between IPv4 and 6 is that we do not use broadcast here anymore. Instead, we use the multicast. Okay, so this is the IPv6 multicast address that we want to send the packet to. Okay, and that IPv6 multicast address is then mapped to an Ethernet multicast address. So if you look at the mapping here, it is basically, it takes the last part of the IPv6 address in front of it. Okay, and that becomes the destination Ethernet multicast address. Okay, so this is a bit complicated, so please stay with me, listen to it again, and also if you are still confused, you can look at the PDFs that we will be sending out to you. In that you will be able to understand how exactly the Ethernet address and the IPv6 address is used to map with the hardware address. Okay, so the source MAC address is the sender's MAC address just like before, and the ether type is the standard IPv6 packet. And there is nothing special here. It's a normal IPv6 packet. So there is no special Ethernet protocol needed here. Like in ARP, like in the IPv4, there was a special protocol ARP, which was present in the frame. So that is not needed here because IPv6 packet itself can handle this request here for the neighbor discovery. So now let's see how the reply packet will look like. It is processed and it's sent back, and the reply is again a standard IPv6 packet with an ICMP6 payload. So here the source address, hopefully the one we are looking for, and the destination addresses of the requester. So there are some flags set out over here. That is the router flag, means that the reply was sent by a router. Then there's a solicited flag, which means that there's an existing entry that needs to be replaced. And there's an override flag also, which means that the existing entry should be replaced. And the solicited flag actually means that the reply was sent, but because it was because someone asked for it. Okay. So the target IPv6 address is again the requested IP address, the one we were asked for, and the Ethernet MAC address is what actually we wanted, and it is included in the IPv6 option. So it contains the same information like we seen in the IPv6 ARP packet, just organized in a different way, and no broadcast is used. It is using the standard IPv6 packet without any special protocol. Okay, so let's now see the comparison between the IPv4 and IPv6 packet. So in IPv4, we were using broadcast, right? A broadcast goes to all the stations on the LAN. And in IPv6, we use multicast. Okay, and multicast packets goes to a specific multicast groups only, right? And if you look how multicast is calculated, there's a good chance that package only goes to the one station. And in some cases, if there might be two different stations that ending in same bits, then but it's still far better than having a broadcast landing into two different stations. Okay, so looking at the stations involved in IPv4, we see that all the stations all the time receives the ARP request, even if they don't intend to, and because they are using broadcast. But in IPv6, only a limited group receives the packet, often just one station at a time. That is actually requesting the broadcast, the Ethernet address for the lookup. So here IPv6, like you can see, it clearly wants in this comparison. So now the protocol that we are using in IPv4 is the ARP, which is a separate protocol. But in IPv6, we use ICMP6, which is a part of IPv6 itself. So again, from a standardization point of view, also IPv6 wins this. So let's conclude this topic for today. Let's see what we talked about in a short summary. So to conclude, we talked about learning Ethernet addresses for IPv4 and IPv6. To send traffic over an Ethernet to an IP node, which the sender first needs to know that the Ethernet address of that node. Okay, IP version 4 and IP version 6 solves this problem in different ways. Then IP version 4 we uses ARP, that is the address resolution protocol on top of Ethernet, and IP version 4 broadcasts ARP requests and receives ARP replies. On the other hand, IP version 6 uses ICMP version 6 for neighbor discovery, and IP version 6 sends neighbor discovery request to a multicast group where it knows the receiver is listening. So this is how Ethernet addresses are learned for IP address in IP version 4 and IP version 6. Okay. So that was about it for the topic for today. I hope it was a good informative topic for everyone. If there are any questions, we are open for it. If anybody is having, I believe this topic was straightforward. Do drop your email IDs in the chat box so that our team can send you the PDFs or the PPTs that are required for this presentation so that you can also get an understanding. Also, the PowerPoint slides includes the reference, the links also that are linked to the RFC so that you can actually see what is exactly in those requested comments also. So reading an RFC actually clears much of the doubts pertaining to those protocols, because we generally use RFCs to see for the content and use in our webinars basically. So this was not too much of a basic topic, but it was quite essential for our understanding that how ARP requests are generally handled over an IPv4 and V6 segment. So majorly ISPs which we are catering can understand now how exactly those requests are getting handled over your LAN segments and how those IP addresses are resolved over your local IP segments also.
Thank you for watching.